Welcome all to this presentation of mine. My name is Campilho. I come from Portugal, ISEP and R.D.S.G. This work deals with the cohesive zone modeling analysis of the impact strength of steel adhesive joints, and more specifically, the cohesive zone parameters influence on the numerical predictions. This is the outline of my presentation. I'm going to begin with the objectives. The impact CCM is going to be validated on the first hand with experimental results, and then a numerical work will take place to analyze several different conditions in the numerical simulations. The stiffness of the cohesive law, decoupling the tension and shear modes in the CCM modeling, cohesive law shape, damage criterion, damage initiation criterion, damage propagation criterion, and then the conclusions. The main objective of this work is to analyze the influence of all these parameters in the CCM impact strength prediction of bonded joints. We are going to consider three different adhesives: AV138, which is a brittle adhesive, Sika Force 7752, a ductile polyurethane, and the high strength XNR 6752. Validation is going to be made with single lap joints with steel adherence and a few different adhesives. RLD AV138 is the same, but the other two are different. In this validation, we are comparing the experimental reference and the numerical reference from a previous work with the numerical simulations carried out in this work. We can see that for the XNR adhesive, the match is good between the numerical results and the numerical reference, although slightly higher than the experiments. The same happens with the AV138, numerical reference, experimental reference, and the numerical reference with the estimated properties for this adhesive. And finally, for the adhesive DP 8005, the numerical reference, which is in agreement with the numerical result, and the comparison with the experimental reference. So we consider that the CCM model is validated for impact testing, and we are now going to do a purely numerical work on the CCM conditions with 4 overlap lengths and the 3 aforementioned adhesives. We begin by evaluating the effect of the elastic stiffness of the cohesive law for the AV138. This line are the reference results compared to the initial properties, and we vary the properties from 0% of the original ones to minus 75% and doubling the initial properties. We can see that for this adhesive, the elastic stiffness does not have a significant influence because we had a variation of 11% maximum of the elastic stiffness if we reduce 75% the elastic stiffness. So this parameter does not influence a lot. The same occurs for the 7752 adhesive. Here the maximum difference is 13%. And also for the XNR adhesive, here the maximum difference is 3.68%. So this parameter does not influence a lot the results. The opposite occurs if we decouple the loading modes in the cohesive zone modeling. So now we are not considering criteria to combine damage initiation and damage propagation under mixed mode. We are separating tension and shear modes. We can see here that there is a significant difference from the reference results, which is this line, and the uncoupled results with a maximum difference of the AV138 adhesive of 26%. The same occurs for the 7752 with a difference of almost 30% and a difference of almost 40% for the highest strength adhesive. So this is not a good policy to uncouple the loading modes under impact loadings. The cohesive law shape, we tested 3 different shapes: triangular, exponential, and trapezoidal. And we can see that under impact, there is not a significant difference between the 3 results, between the 3 loading modes for the AV138. The same occurs for the 7752. Here the results are very similar because this adhesive is less stiff than the other ones and the influence is lesser. And the results for the XNR adhesive also, we don't have a significant effect of the cohesive law shape. We also tested different damage initiation criteria, the quadratic stress criteria, maximum stress criteria, maximum strain criteria, and quadratic strain criterion. We can see that the reference results for the Quad-S criteria, they are almost overlapped with the max-S criteria, while the criteria based on strains, they highly overshoot the experimental values. So these criteria are not suitable for strength prediction under impact. These results are the for AV138. Here we have the results for the 7752. The results are qualitatively similar. The strain criteria do not work well for these joints, and the same results for the XNR adhesive. The strain criteria highly overshoot the expected values. Finally, we tested different damage propagation criteria under mixed mode, more specifically power law criteria with this shape. We tested different power law coefficients and compared to the reference result, which is this one, power law equals to 1, we can see that increasing the exponent brings little difference, while reducing the exponent highly underpredicts the results. We also tested the BK criterion, which is the Benzegar-Canane criterion, and the results are mostly similar, although slightly underpredicted for a BK 2.5. The same for the 7752. Here the results are practically the same, disregarding the exponents of the power law and the BK criterion. And finally, for the XNR, we also have under predictions for the power law 0.5 and slight over predictions with the BK criterion. So highly fear the conclusions that summarize what I said in the presentation, and I would be available for any questions that the audience might have. Thank you.